Hello everybody, this is Mr. Molocash. This is our video for week 11 in Math 172. I want to remind everybody that's watching this video that you can email me at jsmolokach@johnstoncc.edu. Preference given to my students this semester for Math 172, but feel free to ask. This week we're going to start talking about polar coordinates. So this is our list of stuff that we have to do. In this video we're going to be plotting points in polar coordinates. I'll explain what that is. We're going to convert from what's called rectangular coordinates to polar coordinates using special angles. And what we mean by special angles are the ones that are on the unit circle, pi over 3, pi over 4, etc. 5 pi over 6, and so on. Then we're going to convert some polar coordinates back to rectangular coordinates. And then we'll have equations to work with. You get some neat graphs when you graph a polar function. And we won't explain all of that this week, but you can get some really neat graphs, and I'll explain that in a minute. But we'll convert what's a rectangular equation in polar form, and then back from polar form to rectangular. Okay, so the first thing we'll do is show you some polar graph paper. This is what polar graph paper looks like. There's 6 different grids. So instead of having your x and y axis with squares, you still have your x and y axis, but you have these concentric circles. So the one in the first one out from the origin is the unit circle. That's the radius 1. The next one is a 2-unit circle, which is radius 2, and 3 units and 4 units, and so on. So one coordinate that we use to graph in polar coordinates is the r value. R stands for radius. Okay? And then so we need to know how far away we're going to be from the origin. That's the r value. 1, 2, 3, 4, 5, and so on. And we also need to know the angle. And if you're familiar with the unit circle, you remember that 0 degrees is at the positive x-axis, and the positive y-axis is pi over 2 radians, or 90 degrees, and then this is 180 degrees or pi radians, and so forth. And you can even have negative angle measures, and you should know what that means by now. Okay, so we need to know what angle we're going to be going and how far away from the origin we're going to go. This is very different from x and y coordinates, which looks like this. So in x and y coordinates, what happens is, and I see there's like a little bit of a shadow or something on my grid here, but anyway, I'll try to still use this. In x and y coordinates, these are called rectangular coordinates because any point that you put on the grid, you can draw a box between that point and as the opposite corner of a rectangle between that point and the origin. So like for example, the point 3, 2, you go to the right 3 and up 2, and this makes a rectangle, right? So that's why these are called rectangular coordinates. You can only move left, right, up, and down in order to get from one place to another. Certainly you can draw lines and you draw parabolas and things like that, but as far as where points are located, we always describe them in rectangular coordinates. So that means we go to the left and right first, and we go up and down. And of course, we know that x and y can be negative because these are directed distances. So what that means is, if x is negative, we go to the left, and if y is negative, we go down. The opposite direction from positive is negative. The opposite direction from positive is negative. That's going to be the same thing that happens in polar coordinates. So, believe it or not, r can be negative. The radius of the circle can't be negative, but your position with respect to the origin can be. So r is, maybe the angle is pi over 6. Well, if the angle is pi over 6, then positive r would be going toward the angle, like to the right, and then negative r would be going off to the left. So it's kind of like what's going on here is you're taking your x-axis and you're rotating it. You're rotating that x-axis at an angle, so r is positive goes towards the angle, r is negative goes backwards away from the angle. So that's the way you should kind of think about this. Alright, so what we're going to do first is plot some points. And when we plot these points, the first coordinate is r, and the next coordinate is theta. Now this is going to be done backwards from x and y coordinates. In other words, what I'm going to do is I'm going to find out where this angle is first and then go this far toward that angle. So for the point A, I want to find pi over 4, and I'm going to give you guys a link to some polar graph paper that you can print out. In fact, this very same thing. And you can see that this is 30, this is 60, and this is 90. So the 45-degree angle would be right here. So this is where pi over 4 would be. Okay. Now 2 units, r equals positive 2, I would need to remember that this is the positive side of that axis, that rotated x-axis, if you will. So these are the positive numbers. If r were negative, I'd be going this way, away from that angle. So I want positive 2 units toward that angle. So this is where point A is. Okay, so that's the location of the ordered pair r equals 2 and theta equals pi over 4. And again, you find that angle first before you go that far away from the origin. Another way of doing this is you can say, okay, which circle am I on? I'm on the second circle, and then I find that angle on that circle. But you run into problems when r is negative if you deal with things like that. So always use the theta first, find the theta, and then use the r. All right, let's do the next one. So we're going to still have the pi over 4 radians. So same rotation of x-axis, but when r is negative, we're going to go this way. So negative 2, that would be point B. Okay, so pi over 4 is up here. The positive r's go toward pi over 4. The negative r's go away the other direction on the other side. And remember, this is the same thing as x is positive, x is negative. So negative is like going away from the positive. It's repelling in the opposite direction. It's kind of what's going on here. All right, so you might want to ask, oh, what happens if theta is negative? Well, you should already know that. Theta is negative means we go backwards around the circle, or what I mean by backwards is clockwise as opposed to counterclockwise. So this is where negative pi over 4 would be. So this is our angle that our positive numbers are headed toward. The negative numbers would be headed away from that. Since r is positive, we're going to use this point as the location of point C. So there's C. Okay, again, negative pi over 4 is the angle, 2 units toward it. And then what happens if they're both negative? Well, you go clockwise with your angle and then 2 units away from that angle. So D would be up here. Okay, so I would encourage you to go back and rewind this video and watch this. Maybe watch some other videos about plotting polar coordinates and get as many examples as you can. Use the textbook. This is very different than maybe anything you've ever learned before. So don't get overwhelmed or freaked out by this. You will eventually get used to it. But this is a very different way of plotting points than with x and y coordinates. Okay, so I know that this is going to seem like a little bit of shock to you right now because this is a little weird, but you know, trust me, you'll get used to this the more practice you get. Okay, great. So the next thing we're going to do is we're going to convert between these r's and thetas and where the x and y would be. So if the graph paper had squares on it, like where would that point, how far would it be in the x direction and how far would it be in the y direction? Or vice versa, like if we had points like the point 3, 2, what circle would that be on in polar coordinates? So we need to be able to translate between these two things. And a very important way to do that is to consider this triangle. Okay, so let's say that we have point O. Point O is the same thing as the origin. That point O is that same point right there. And P represents a point anywhere. It looks like I've drawn it in the first quadrant, but it could be any point anywhere on the graph. So if you pick a point, say in the first quadrant, and you draw a line segment between that point and the origin, that length is r. We've already explained that before, right? That length is r. And then theta is the angle that's made between the positive x-axis and the line segment that you drew, okay? And this is an angle in what's called standard position, if you remember that from earlier, okay? So for this one, it looks like theta is positive, right? Because I'm going upwards or in a counterclockwise direction. Now, if I wanted to get to that point in this kind of graph paper, let's say that point P is up here somewhere. The only way to get to it would be to go to the right x units, x number of units, and then go up y number of units. Well, these two kinds of coordinate systems are related to each other by this triangle, okay? And it's important to see some relationships in this triangle. First off, you can tell that x squared plus y squared equals r squared. And this is true because of the Pythagorean theorem. A squared plus b squared equals c squared. So if you know x and y, you can find out what r is. This is going from rectangular to polar, right? Well, how do we find out what theta is? Well, if we only know x and y, and we got to find out theta, then we can use the tangent function. The tangent of theta is the opposite over the adjacent, and so that's y divided by x. And you probably remember that from an earlier study of trigonometry. Okay, so these two formulas are to go from rectangular coordinates to polar coordinates. And when you do this, you have to be a little bit careful with theta, because remember that tangent is positive in both the first and third quadrants. So you have to check your x and y and see what quadrant you're in before you find your angle. But other than that, these pretty straightforward. Just plug your x and y in and do inverse tangent. Plug your x and y in, square, add, do the square root like you would for your Pythagorean theorem. All right, so what if we have to go the other way around? Well, this is how you would do it with the other way around. You would take your theta and first find the cosine of it, right? So in this triangle, the cosine of theta is the adjacent over the hypotenuse. Well, we can multiply both sides by r, and the r's cancel out, and so one formula we can use is that x is equal to r times the cosine of theta, because the r's cancel there, right? So if we know, and my folded paper is becoming unfolded, sorry, but if you know what r and theta are, you can definitely find out x. You plug your r in and you find the cosine of theta and you multiply and you get x. Well, you could probably guess how I'm going to find y. Instead of using cosine, I'm going to use sine. The sine of this angle theta is the opposite over the hypotenuse. And so multiplying both sides by r again, so I can solve for y, I get y is r sine theta. So if I put my r and my theta here in this little formula, I can find out what y is. All right, so the formulas on the left are to be used to go from rectangular coordinates to polar. The formulas on the right here are to be used to go from polar coordinates to rectangular. Okay, so you're definitely going to want to have all this written down, especially these formulas. You're going to be using them quite a bit. All right, having said that, I'm going to fold this down. We're going to do some examples. Now, on formulas, you might be able to kind of see them through the paper there because I'm using this felt tip pen, but if you need the formulas, rewind the video, go write them down, and then come back. Okay, so here's an example, right? Let's convert the ordered pair in x and y, 2 square root 3, to what we call polar coordinates. So what this means is that somewhere on a graph, okay, from the origin, I'm going to the right 2 and up the square root of 3, which is like 1.7-ish. So this point is right there, to the right 2 up square root 3. But what I want to figure out is the r value and the theta value, right? I want to find out. So I know x and y. I want to find r and theta. The way to do that is to use these formulas right here, right? All right, so the first thing we're going to do to find r is we're going to use x squared plus y squared equals r squared. X squared plus y squared equals r squared. So that's 4. Square root 3 times itself is 3. And 4 plus 3 is 7. And I'm going to do the square root of both sides. And we're going to let r be the positive square root of 7. Okay, so that's what r is. Well, how do we find out what theta is? Well, the problem with theta is you're going to want to know the inverse tangent of this thing, right? So we're going to say the tangent of this angle theta is equal to square root 3 divided by 2. Now, why is that there and why is that there? Because y divided by x, right? So our theta is going to be the inverse tangent of this square root 3 over 2. And this works out to be some weird radian measure that we don't know on the unit circle. So let me go type this in my calculator. Okay, so this turns out to be 0.714 radians. Okay, so there's our angle. So the coordinates are square root 7 and 0.714 in r and theta. Okay, that's the answer for this. Now, most of the time, and especially if you're one of my 172 students, you're going to be finding this angle is a special angle on the unit circle. So you can find this straight off of the unit circle. It'll be pi over 4, pi over 6, something like that. When you're doing the inverse tangent in your calculator, you're going to get a decimal number. But, you know, let's say if this were square root 3 over 1, right? Let's do this whole problem all over again where this were 1. All right, so let me get a new sheet of paper and let's do that one. So let's say that we wanted to go xy is 1 square root 3, and we want to know what r and theta are. Okay, so x squared plus y squared equals r squared. So we do 1 squared plus square root 3 squared. That's 1, that's 3, and we get 4. And the square root of 4 is 2. Now we technically could put plus or minus 2, right? But remember, the minus 2 is going to go away from the angle, and we want to stay in the first quadrant. So we're going to choose r as positive 2. All right, the tangent of theta is y over x, right? And that's the square root of 3 over 1. And a trick from the unit circle here is in the unit circle, we have these 3 things here, right? So this is 1/2 square root 3 over 2, and this is square root 2 over 2 and square root 2 over 2, and this is square root 3 over 2 and 1/2, and I'm sorry if you can't read that, but hopefully you get the idea. And a trick here is that you can divide in this fraction, you can divide both the top and the bottom by 2, and this top number tells you the sine, and the bottom is the cosine. So that would be this angle right here, which is pi over 3. Right? So our theta would be, just by inspection of the unit circle, pi over 3. So this would be 2 comma pi over 3 would be the r and theta angle when x and y is 1 and up square root 3. Okay, so now what we need to do is go the exact opposite way, right? What we need to figure out now is what happens if we already have r and theta. If we already have r and theta, let's say r and theta is 2 and pi over 4, the very first point we plotted in the first quadrant. We want to figure out what x and y is, right? So for those, remember, if we know r and theta and we want to figure out x and y, we use these two formulas right here that you wrote down earlier. R and theta is known, we want to figure out x and y. So we plug in your r and theta there, right? So straight away, r cosine theta is x and r sine theta is y. And this is a special angle, so we know the unit circle values for sine and cosine. I drew them on the last piece of paper, so this cosine here is square root 2 over 2, and the sine is also square root 2 over 2. And the 2's divide to become 1, so this is square root 2, and so is this. So the rectangular coordinates x and y are square root 2, square root 2. Okay, so what that means is that this point that we plotted earlier, right here, you wouldn't go to the right 2 units and up 2 units, then you'd be, you know, up here a little bit. So you'd go to the right square root 2 units and up square root 2 units, and you'd be right at that point, which is 2 units away from the origin. Okay? So that's kind of how it is with converting between rectangular and polar coordinates. And I think it's time now for a little bit of comic relief. Polar coordinates are best used when things are round, and Cartesian coordinates are it's another name for rectangular coordinates when things are boxy, right? So, you know, when you're going straight right and straight up, it's rectangular Cartesian. When you're going around at an angle and straight to the place that you want to go to, then it's polar coordinates, right? So it's kind of interesting how that works out, right? I don't know if you think this is funny or not. It's kind of a math geek joke, but you can find that on the internet, and I'll put a link to that where I found that picture in the video description. Okay, so what we need to do next, okay, we've been able to plot points in polar coordinates. We've been able to convert between rectangular and polar, and we've indicated when that happens with a special angle. And if we had a polar coordinate, set of polar coordinates for a point, we can convert to rectangular, so we showed you that. But now we have these equations to deal with, and this is where things get really, really fun looking, okay? So right off, I'm just going to go ahead and give you an example. And here's my first example. All right, convert x squared plus y squared equals x plus y to polar form. And you may be saying, whoa, I've never seen an equation that looks like that. What the heck is that if I graph it? Well, you can let me put a little plug in for my favorite graphing calculator. You can always see what the graph looks like by going to http://desmos.com/calculator. Great website. If you do that, you'll be able to just type in the equation as is. You don't even have to solve for y. Good luck solving this for y. It's kind of a pain. You're not going to be able to. And this graph is definitely not a function either. It doesn't pass the vertical line test. But Desmos will show you the graph. It will show you what that looks like. And it's a circle. It's a circle like in the first quadrant. So the question is, what would that look like if we used a polar form? Okay, so let's define what we mean first by polar form. Okay, the polar form can only have r's and thetas in it. No x's and y's allowed. All the x's and y's have to be kicked out and replaced with r's and thetas. And if you look at a function in polar form, we definitely can't use a vertical line test to define a function, but you can say r is a function of theta. R is a function of theta, which is kind of weird because in x and y is a function of x, but in r and theta, r is a function of theta. So it's like the range variable is first and then the domain. The domain is on the right, the range is on the left. In x and y, the domain is on the left and the range is on the right. But anyway, that's kind of what's going on there. So what we're going to do is we're going to go remember all those formulas I told you to write down earlier. And in order to get rid of x and y, we can replace them with these things. So these formulas, oftentimes, they work in reverse when you're dealing with equations, okay? When you're dealing with equations. And you'll see why when I do this example. So I'm not converting from r and theta to x and y. I'm converting from x and y to r and theta, but I'm still going to use these two formulas. And I'm going to use these two, not the tangent one. But first off, the first thing I notice is that this is r squared. Okay, that was formula number 1 in the upper left-hand corner. X squared plus y squared is r squared, so those x's and y's are gone. But I can't replace this with r squared because the x's and y's aren't squared. So what I have to do there is have to replace the x and the y individually. X is r cosine theta plus, from the plus sign, and then y, remember, is r sine theta. And in order to get r by itself, I can just divide both sides by r. So I get r equals cosine theta plus sine theta. Okay, and believe it or not, the great thing about the Desmos calculator, and let me go plug that little website one more time. Go to that website, maybe open it in another tab while you have this video paused. You can type this equation, r equals cosine theta plus sine theta, and compare the graph to the graph of this thing. So you can type this equation out and it will show you a graph, and again, it's a circle. And this will give you the same graph. It will overlay over the top of the same graph, which means you got the conversion right. Okay, so two different ways to describe the same graph. One is in polar form, which looks really messy. I'm sorry, rectangular form, which looks really messy. But the polar form looks a whole lot nicer. It's just cosine theta plus sine theta. So that's kind of how that works. Okay, here's another example, which is a little bit more challenging. Okay, so convert x plus y quantity squared equals 4x plus y to polar form. Well, be careful with this, right? It's not x squared plus y squared, so I can't just go right off and replace this with r squared. What I need to do is square this out, and I'm going to trust that you know how to do the FOIL method. X plus y times x plus y, you'll get this, all right? And the reason I'd wanted to do that is because this is r squared. So again, now I can take my x squared plus y squared, and I probably should have circled the plus as well. So all that stuff becomes r squared, right? So what's this other stuff? Well, it's 2 times x, which is r cosine theta, times y, which is r sine theta. And what's this over here? This is for x, which is r cosine theta, and plus y, which is r sine theta. Now, there's a lot of stuff that needs to be done here to simplify this. But I will say that all the x's and y's are gone, and technically we're already in polar form. So if this is as far as you can get on the next test, this would be counted correct. However, you can simplify this. So I'll show you that, especially if you're watching this and you're in another math class besides mine. So this would be r squared plus 2r squared cosine theta sine theta equals 4r. Oh, actually, let me factor the r out. Sorry. Let me factor the r out. Okay. Now we can divide both sides by r. So these r's cancel. And then this becomes r plus 2, well, plus another r. And then what's left over is 2, I'll write this as 2 sine theta cosine theta. And over here all the r's are gone. And you might remember this from a recent lesson, right? This is r plus r times sine 2 theta. And here we can factor out the r and get 1 plus sine 2 theta. Now that may be a little confusing why I did that, but remember r times 1 is r, and r times this other thing is r times that other thing, right? So we'll just divide by the stuff that we don't want on the left side, and we're done. Okay, so r is this not so fun looking expression over here. But you get a really cool graph if you graph this in Desmos and you graph this in Desmos and you compare the two graphs, you get the same thing, and it's a rotated parabola. It's a parabola that's kind of like rotated like this. It's pretty cool. So again, if you got this far, then that's cool. But if you can get this far, that's even better, and Alex will like you better if you're an Alex student. All right, last example. What if we have a polar equation and we want to convert it to rectangular form, right? Well, remember the trick I used for this double angle formula, right? And by the way, if you go graph this in Desmos, this is a really cool graph too. It's called a rose. The graph looks something like this. I didn't draw it perfectly, but it's supposed to fit inside a circle of radius 2. Right, so the radius is 2. And the 2 theta makes all these little 4 petals of what's called a rose. So this is called a rose curve. Pretty neat looking curve. And what we're going to do is try to write the rectangular form of this. And I will warn you that this is going to be messy. Okay, so hang in there. The first thing we want to do is change this to 2 sine theta cosine theta. And remember my formulas from earlier. I had a formula that had r sine theta and r cosine theta, but over here there's no r's, right? So what I'm going to do is put them there. I'm going to say that 2 times 2 is 4. I'm going to put an r there, and if I put an r in front of that sine theta, I need to put 1 over here too. I also need an r in front of the cosine theta, so I'm going to put another r over here. So these two r's and these two r's match. Everything else, and I don't know if I can block all this or not, but everything else is what was up there. 4 sine theta cosine theta. So I multiplied both sides by r squared. Okay, great. So the left side is 4 times x times y. Remember that x is r cosine theta and y is r sine theta, and that's the reason why I did that trick. But over here I've got r cubed. R cubed. Well, if it were r squared, that'd be really nice. I know what r squared is, but I don't know what r cubed is, right? So what I need to do is I need to make that exponent positive and even. Well, it's odd right now, but to make it even, I can multiply that exponent by 2. The way to do that is to square that side. If I square that side, I have to square this side. So this is r to the 6th, and this is 4xy times 4xy, which is 16x squared y squared. Now, r to the 6th is r squared cubed, right? Well, what is r squared from our formulas? That's right, it's x squared plus y squared. So, as ugly as this is, that's the rectangular form of our rose curve. And you can test this out, right? You can graph this in Desmos. You can graph this in Desmos. And you can compare the two graphs. Now, why am I asking you to use Desmos? Because, well, your scientific calculator doesn't graph anything, and even your TI graphing calculator or whatever, it will not graph this at all. The only way to do it is to use Desmos. So great, wonderful tool. Again, let me go plug that. Desmos.com/calculator. We did our conversions. Have questions, shoot me an email, write in the discussion board. Hang in there, work hard, have a great week.